Okay, so our topic today is the design of safety instrumented systems. The words that I use for a long time is interlocks. So how many folks in your plants have safety interlocks? Okay, so we've got a lot of these. So the topic today is how do you decide or how do you go about recommending what you're going to do when you design one of these things. So let's talk about a typical problem. You have a LOPA team, layer protection analysis team, and you've done a review, and somebody comes in and says, we need a SIL 2 interlock. Have you heard these kind of words before? Yes? Okay. So that means that the probability of failure on demand as calculated by the methods outlined in the standard has to be between 10 to the minus 2 to 10 to the minus 3. Or in reciprocal terms, that means that what they refer to as the risk reduction factor for the interlock has to be between 100 and 1,000. Okay? Now, the control group comes in and you are the process side. And they give you a proposal. This is what we're going to do to install this interlock. And you've been asked to go through and look at this. Your boss says, is this going to achieve what you want it to do or not? That's a fairly normal question. So what are you supposed to do? So here we have the description of what this interlock looks like. So this one is a classic simple problem. The problem is I've got a compressor. I'm going to not want to put liquids through a compressor. When you put a big slug of liquids into a compressor, the compressor doesn't like it and it typically tears it up and blows the compressor up. This has been tried experimentally all over the world and it works almost every time. Now, so what do? We put in a tank. In this case, it's called a compressor knockout drum. The tank has a high-level set of instrumentation. It goes to a box, a piece of electronics, a computer that is called a system, a safety instrumented system, basically a logic solver. The logic solver in this case comes out and fires a couple of relays. These are technically called interposing relays, and they basically turn off the power to the compressor so that we don't slug the liquid in it. So that's the design. In block form, the control people like to look at what is called block diagrams. So we have a block that says sensors, and we got 2 out of 3 voting on the sensors, the level transmitters. We got a sys box, safety instrumented system logic solver. We've got in the field then we have 2 interposing relays, which is R1 and R2. Where the way this system is set up, it's going to be 1 out of 2 voting, which means that either one of the relays says turn it off, it turns it off. And we got 1 out of 1 voting on the MCC. By the standard, the IEC 61511 standard, which is equivalent to the ISA S8401 standard, these are standard numbers. They're required to do a bunch of calculations. They do the calculations, they come back in, and they report to you as the process engineer / manager that the risk reduction factor for this design as proposed is 1192, and this means that it is SIL 3, right? Everybody seen this kind of thing appear? Okay, so let's talk about what are the problems with what is being done very commonly. Typically what you're doing in the field, what the people, the controls group are oftentimes doing is they're grabbing numbers either out of a generic database, and there's a whole bunch of them. I've got a shelf full of books, and there's computer software, variety of things like ORITA, and there's the reliability data center, and there's vendor data. There's piles of data. So they grab a number out of those, or they get vendor-specific data. And they do all these calculations, and the calculations result in numbers that look like that. So the question is, Do we believe these? So let's talk about problems. The first problem is that there is massive uncertainty in the data. That the first problem is that all of these values that are reported, these are not experimental values of the vapor pressure of water at 100 degrees centigrade. It's not a precise measurement. These are statistical quantities at best. And so we have uncertainties in the diagnostic coverage of, that's a term in the computer of the SIS, the time that you're going to test it. If you say I'm going to test it every 2 years, what do you really mean? I'm going to test it between 18 months, 28 months. It's not 2 years, there's actually a range, right? So we have all kinds of uncertainties all through these calculations. And so what people have done typically is they grab the numbers out of the tables and they do the calculations. So let's start with the simple thing first. If I do the calculation in the middle of an uncertain set of parameters, right in the center, that is called the mean. This is the normal distribution. Okay, there's another thing that we'll talk about in a minute called the mode. The mode is the most frequent number. So if I do the calculation right in the middle, what is the likelihood that that number that you selected is at least as good as what you want it to be? It's 50%. Half of the curve is on one side of the mean, half of the curve is on the other side of the mean. Okay, so if you design at a point right in the middle of your curve, then half of the time it will work better than what you expected and half of the time it'll work worse. Now, there's lots of probability distributions. Unfortunately, our equipment doesn't follow this thing. What it actually will follow is something that looks like this. So this is a distribution whose name is called the log normal, but you don't care about that. The key thing that you need to know is that the mode, which is the most frequent value and which is often, but not always, the numbers tabulated in the databases, is the mode. But the thing that actually determines how well the gadget's going to work on average is the mean. And they can be dramatically different. This is a case that I just put together, and the mode is 10, the mean is 50. If this is the failure rate, the average failure rate is 5 times higher than the value that would be in the table. Now that ought to spook you some, okay? Because you need to understand precisely what the data mean that you're using. Now, I'm going to attempt in about 2 minutes to give you an understanding of a branch of mathematics called the algebra of random variables. I've got 3 equations, so just bear with me. Any arbitrary function that I'm going to work with, where I've got a function of some group of random variables, and I've got an output, and I'm going to call it y equals f of x, just like you saw in your first semester of calculus, many years ago in school, that I can go through and I can calculate the mean of y, and I'm going to use some things called operators. So E of y is the expected value of y, which you guys call the mean. That is equal to, very good approximation, the function of the expected values. And that's exactly what you do when you do calculations. You take the average value of some variable and you calculate it, and then you get the average value of an output variable. This is what you do all the time. What you don't do all the time is this. Right? If I want to calculate a function called the variance is the square of the standard deviation. Okay? So the variance is basically the weighted variance contribution for each of the random variables. So that little partial derivative of y with respect to x of I squared, that's simply the weight, how sensitive your output is to the input. So the more sensitive the variable is, the more uncertainty that is created by uncertainty in that variable. Okay? Now, that's so much for mathematics. Now, in the paper, which is in the online proceedings of this, all of this has gone through in horrible detail that will explain in great depth how you do all these calculations, but that's all I'm going to show you in the presentation. Let's look at the results. To begin with, we have to start with trying to understand what the distribution is that we're going to work with. I like simple. So the distribution that I'm going to work with in this model is what is called the triangular distribution. It has three parameters, a minimum, a maximum, and a mode. This corresponds very closely to what you see in the data tables that you'll have presented in all of these databases. There's a whole bunch of other distributions. There's chi-squared. There's a bunch of distributions that could be. This is the simplest one to explain to somebody. This is the one we use. Now, here's the kind of stuff that you get when you go into the database. If you look at the failure rate of devices for the level transmitters, the minimum for the ones that we picked is like 2 times 10 to the minus 3. This is the probability of failure on demand of the device. The maximum is 8 times 10 to the minus 3. The mode, the tabulated value, is 5. Since these are pretty close to being the same, then the average, the mean, is 5.4, and we calculate the variance. And we can do this for all of the uncertain parameters in the model. So all of the parameters that we have that I just showed you and a bunch of other ones that I haven't showed you, we can go through, pull the data out of the tables, calculate the mean and the variance, and then we can put them together. And here's the kind of thing that you get. So there's different ways of doing the calculations at the end. One way is a method called Monte Carlo, where we just randomly select things. Okay, this Monte Carlo simulation I set up, and I had it test 100,000 versions of this interlock. So it did a Monte Carlo with a number of trials, 100,000. This is the output result. The red dotted line is the target. That's the 10 to the minus 2. Everything between 0 and 10 to the minus 2, everything to the left of 10 to the minus 2 says the interlock is okay. Everything to the right of 10 to the minus 2 says that the interlock is not okay. So the area under that curve represents the fraction of time that when you install this design that it won't work at least as well as what you wanted it to work. All right? So this ought to be disturbing, because what this means is that the design that was brought to you by your control group is not going to satisfy the requirement that your layer protection analysis group asked you to have. Okay? Now we can actually go through using fancier math than what I've got up on the board right now. We can go through and calculate a whole bunch of stuff. Some of the stuff we can calculate is that what is the mean probability of failure on demand of this interlock? Well, the RRF is 128. If I did the calculation based upon yanking the numbers right out of the tables, it was 1192. There's almost a factor of 10 difference. The interlock you're really going to get is 10 times worse than the one you got using the tabular data. But it's worse than that. If I say that I want to have a 5% chance that the interlock will not work at least as well as I want it to work, then the RRF is 59, and the thing that we thought was SIL 3 is actually only a mid-range SIL 1 device. If I'm saying I'm willing to take a 30% chance that the interlock will not work correctly, then the RRF is 93, and it's a high-range SIL 1, almost SIL 2, but it does not meet the criteria that your LOPA team specified. Now, we can go through, in the paper, we go through and we can find out that the causes of all of this are the failure rate data for the MCC, the failure rate data for the relay, and to some extent the test interval. When I had a control engineer in Angela's organization review this, his response was, garbage in, garbage out, you're using lousy components. That's a fact, okay? But this analysis will tell you that I need to switch and buy some better hardware. Conclusions. If you really want to do what we've got here, there's a 30% chance that it's not going to work when needed. If you're willing to, you want to make sure that it'll work, then I'm going to have to say this is only SIL 1 and it doesn't satisfy our requirements. If I want to get it better, I've got to buy some better equipment. That is the MCC, I'm going to have to change it out. That's the switching equipment. I'm going to change the relays out. And the message that I want you guys to take away from this is, when you're doing the analysis, when the LOPA team comes in and says, I want a SIL 2 interlock, a risk reduction factor of 100, that does not mean that the design team designs to 100. That means that they have to design to a risk reduction factor significantly above 100. The working recommendation right now, without analysis, is you design to the mid-range of the thing that you want. So if I want a SIL 2 interlock, instead of having the design team have an RRF of 100, they need to design to an RRF of 500. And I'm not willing, I'm absolutely not convinced that's enough, but we could then find out by doing this kind of analysis if that's enough or not. So the evaluation procedure then is you complete the design, you go through and you define all of the data that you have. You go through and you figure out what the contributions are. The paper explains how to go about doing all of this. And you go through this 9-step process and you can figure out what the uncertainty is that is in your design and what you need to do to fix it. The end result of all of this is that I should have convinced you by now that randomly pulling data out of tables is, without understanding what those data are, is not a good thing to do. You need to really understand what's in there. The best data that you can get on the failure rates of your system, your gadgets, is based upon what goes on in your plant. If you have data based upon your plant, we can use that and with some confidence. If you don't have data based upon what is in your plant and you're using generic data, now you need to do this with very great caution. So I'm basically at an ending point. There's a tremendous amount of detail in the paper. All of the parameters are explained. The calculation methods are done. Calculations are actually done 2 different ways. So I'm willing to take questions.